frequency response of FET amplifier. The objective of this session is analysis of FET amplifier at high frequencies, followed with a numerical example, and also we discuss a frequency response of a cascade amplifiers or multistage amplifiers. Okay, FET amplifier, that circuit shown in figure, this is a FET amplifier. Now we have to analyze this with high frequency response. We know that the diode junction can be replaced with its equivalent model. If you consider a diode, then this diode can be at high frequencies, diode can be replaced with its R and a capacitor C. Therefore, here in this transistor amplifier at the high frequencies, due to this equivalent model of this junction FET, there is a capacitance lies in between the drain and the gate, that is denoted with CGD, and then there is a capacitance between the junction, gate and a source, it is defined with CGS, and also even there is no junction between that an FET model, but due to the leads and then this is acting as a semiconductor bar is acting as a a parallel plate capacitor. Therefore, there is a capacitance is existing, that is CDS. In addition to that, these three capacitance, that this wiring circuit gives provides a capacitance, this is a coaxial capacitance, that is denoted with CWI at the input circuitry, and CW0 is a capacitance of a wiring circuit, that is denoted with CW0. For this circuit analysis, we need to write an equivalent modulet of a transistors at high frequencies. We know that if you consider this transistor model, FET model, then that there is a gate and there is a source. In between that gate and source, this is acting as a open circuit because the voltage drop across is VGS. At the output circuit, there is a current source, this is given by GM into VGS, then this is parallel with a resistance RD. This is the small signal model of a transistor amplifier. At high frequencies, there is a external capacitance, that is there is a CGD and CGS and CDS, and at high frequencies the reactance of this capacitor CC, reactance of this capacitor CG, reactance of this capacitor CS is approaches to 0 XC. Therefore, this RS and CS combination is acting as a short circuit, and similarly that CG and CC are behaves like a short circuit element. Then this using this analysis, you have to only that a high frequency response of an amplifier is depends on that a CGD, CGS, CDS, CWI and CW0. For this, you have to transfer the equivalent circuit. For this equivalent circuit, there is you have to first draw the internal circuit. There is a capacitance between the gate and a source. Therefore, in addition to that, there is a capacitance between this point, this is CGS, and similarly there is a capacitance between the drain and the source, and it is denoted with C, that is C, it is CGDS. Apart from that, there is a capacitor at the output side, that is C W0. Then we can rewrite this circuit, this is gate and a source, this is GM into VGS, then here we have a resistance RD, there is a capacitance CGCDS. In the input side, this is written as means that capacitance is present at this point is CGS and the a capacitance CWI, and also this is source and then this is drain, and also there is a capacitance in between the drain and a source, and it is denoted with a CGD. This is also known as a feedback resistance between the input and the output. This is an equivalent circuit model of a transistor FET amplifier at high frequency. Now we have to connect an external component. To connect an external component, set VDD is equal to 0. When VDD is equal to 0 and these two are acting as a short circuit element, then you are going to get this RD is lies between the drain and a source, and also this RL is also lies between this point, and also there is a capacitance between this point is that is CW naught. Output is to be taken across that point. Similarly, that RG is between gate and a source, and then there is a resistance RS, and then this voltage is Vs is applied. This is the equivalent model of a transistor FET amplifier at high frequencies. If you observe, then there is a voltage up across this point, this resistance RG is nothing but VGS, or this point is also VGS. If you observe this, that capacitor CGD is a feedback between the drain and the gate. This, if you analyze that circuit as it is, then that complexity of the circuit analysis is increases. To reduce the complexity of the circuit analysis, you have to replace this CGD with its equivalent capacitances at the input side and output side by using a Miller's theorem. Hence, you are going to get a CMI input, a capacitance is given by CMI is equal to CGD into 1 minus AB, and CM naught is equal to CGD into 1 minus 1 by AB. Okay. Then this circuit is to be replaced with its equivalent A capacitances. Hence, if you rewriting this circuit, if you replace this circuit with its equivalent circuit, then that circuit looks like this. There is a capacitance is connecting at this point. This capacitance is denoted with CMI, and similarly this equivalent circuit is to be, capacitance is to be lies here. This capacitance value is given as CM naught, where CM naught and CMI are given by this expression 1 and 2. Now this circuit is further simplified. Then we need to determine its equivalent value. To determine means we have to find the objective is to find the what is the high frequency response at due to the input junction, and what is the high frequency response at the output circuitry. First, you have to discuss one by one. For this case, we need to determine the what is the inputs. Okay. For this is acting as a open circuit. This circuit is different and this circuit is acting differently, separately. For this circuit, if you observe, these three capacitors, that is CWI, CGS and CMI are connected in parallel. Then its equivalent impedance is denoted with CG. This is equal to CWI plus CGS plus CMI. Okay. And then also you have to write an equivalent impedance or resistance for this circuit. We are looking into back. This is nothing but Thevenin's equivalent resistance of a network. For the Thevenin's equivalent network of a transistor amplifier network is given by, you have to set Vs is equal to 0. When Vs is equal to 0 means this is acting as a short circuit. Then if you are observing this, means this resistance means when looking at that only one resistance, this is connected in, it is a open circuit, then you are writing this, these two are in series. Therefore, you are going to get that resistance is to be looks like R signal plus RG or RI. Then this circuit, input circuit is replaced with its equivalent circuit, that is Vs supply voltage, and is in series with R signal plus Rg, and then output is to be taken across A C G. Then we need to find the frequency response for this circuit, one step. And similarly, if you are further simplified this circuit at the output stage, if you are further output stage means this C ds C m naught at this point and also C w naught are connected in parallel. Therefore, we can say that output circuitry is given by, that is means we are going to get this RTHI. This signal is to be a parallel combination of this, and then that C naught is given by, a parallel combination of this is given by C m naught plus C ds plus C w naught, and then the resistance RD, this RD and this RD. When you are looking into this circuit, then this is to be a parallel combination of this, then you are going to get RTH naught, because you have to find an open circuited resistance. Therefore, you are going to get this RD is in parallel with capital RD is in parallel with RL. Then the output circuitry is replaced with its equivalent circuit by considering this current source is Gm into VGS, and then is in, because even if you find the RTH naught, because the source is current source, therefore this resistance is in parallel, the resistance with RTH naught is in parallel, and then you are taken this value at this point is C naught. We need to find the response of this amplifier separately. Then this circuit is further simplified. You replace a constant current source with a voltage source. Then using a source transformation, we can replace with this circuit by a source dash V dash in series with RTH naught is in parallel with C naught series. This is the high frequency response of an amplifier. We need to analyze this circuit further for the determining the cutoff frequencies of the amplifier. Let us consider one by one. For the equivalent circuit, we know for the, at the input circuitry, it is given by V S is in series with RTHI. RTHI is with an input resistance CI. Output is to be denoted as VI. Okay. For this case, we need to find an equivalent circuit, then where RTHI is nothing but a parallel combination of RG is in parallel with R signal, and CI is nothing but CMI plus CWI plus CGD. For this case, we need to find the equivalent circuit. For this, you have to apply a KVL to this path, where VI is defined as that I into minus JXCI, then I is equal to a Vs voltage source divided by the total impedance, that is RTHI minus JXCI. If you substitute into the above expression, then that Vi is equal to Vs divided by Vs into minus JXCI divided by RTHI minus JXCI, where that XCI is nothing but a reactance of a capacitor, it is value equal to 1 by 2 pi f into Ci. If substitute this, we are going to get Vi by Vs equal to minus j 1 divided by 2 pi f Ci divided by R T Hi minus j divided by 2 pi f Ci. This is equal to, if you take minus 1 by j common, then you are going to get 1 divided by 1 minus j 2 pi f R T Hi into Ci. Okay. Then this is to be Vi by Vs is complex in nature. For this circuitry, we need to find what is the impedance. For this circuit, the reactance of a capacitor equal to the impedance, then it transfers the maximum power. Means that at a particular frequency, the reactance of a capacitor value equal to the resistance of a amplifier. Therefore, we need to set RTHI by this, then you are going to get that at, we can say that a frequency f is equal to f h I, then this reactance are equal, then you are going to get FHI is equal to 1 divided by 2 pi R THI into Ci. From this circuit analysis, we got the value, the gain of the amplifier Vi by Vs is equal to 1 divided by 1 minus j f by f h I. It is a complex in nature. Then we have to need to determine a magnitude and a phase. Then that magnitude of a network is given by that Vi by Vs magnitude equal to 1 divided by square root of f plus f h I whole square, and phase is a tan inverse of f by fhi. You are interested only in a magnitude of a amplifier, therefore, this magnitude is by this. If you plot a frequency response versus gain a V naught by Vi, then there is at f is equal to 0, this gain is 1 maximum, it is known as a mid-band frequency gain. As the frequency increases, that gain of the amplifier decreases exponentially, and is as the frequency increases, it approaches to the 0. This is value equal to 1. Now, if you set that f is equal to fhi, at f is equal to fhi means I consider this some frequency, this is fhi, then the magnitude of Vi by Vs is nothing but 1 by root 2. For this case, means this gain of the amplifier at this frequency response is given by, this is a gain, and then this corresponding gain is to be 1 by root 2 times. Therefore, this is nothing but the off power cutoff frequency. If you take the log 20 log 1 by root 2, this value is equal to minus 3 dB. Hence, this FHI is to be defined as a minus 3 dB cutoff, upper cutoff frequency of the FET amplifier. And similarly, we can find the equivalent circuit at the output circuit. Output circuit, we defined the equivalent circuit is, this is something V dash, this is nothing but minus Gm into Vgs multiplied with that R T H naught, it is a voltage source, convert a current source into the voltage source, then this resistance is in series with the amplifier, that is R T H naught. Output is to be taken across this capacitor C naught. If you are analyzing this circuit in the similar lines to the input circuitry, then you are going to get a upper V dash V naught by output is to be taken across this point, V naught by V dash is equal to 1 divided by 1 square root of 1 minus J F by F H naught. Okay. Then you are going to where F H naught is given by 1 divided by 2 point only 2 components, resistance and a capacitor. This is equal to 1 by R T H naught into C naught. Then the magnitude V naught by Vi is V dash is given by 1 divided by square root of F by F H naught whole square. Therefore, we determine both the frequency response at the high frequency due to the input frequency component, that CGS and CGD, and also we determine a upper cutoff frequency due to the output at the output circuitry, that is due to the CGD and CDS, that is given by these two expressions. We have done its equivalent circuits already, and then we have discussed the equivalent circuit of the amplifier. Now, we consider the problem where determine the minus 3 dB cutoff frequency of low frequency and high frequency of the amplifier, and also calculate a bandwidth for the given data. VDD is equal to 20, R signal is equal to 10K and RG is equal to 1 mega, R2 is equal to RD is equal to 4.7K and RL is equal to 2.2K, and CG and CC is equal to CG is equal to 0.01 microfarad and CC is equal to 0.5 microfarad and CS is equal to 2 microfarad, where the FET parameters, that GM is equal to 2 ms millisiemens or millivolts per milliamperes per volts, and CGD is given by 2 pf and CGS between gate and a source is given as 4 pf and CDS is equal to 0.5 pf, where that wiring input impedance and the output impedance are CWI is equal to 5 pf and CW naught is equal to 6 pf. For this, we need to calculate the input impedance and the output impedance of our input and output high frequency and low frequencies of the FET amplifier, and also bandwidth. For this problem, that statement you are using for this circuit, if you observe, they are given so many data, that is they are given VDD and other parameters. For the AC analysis, normally that a source DC voltage is not used to applied. This VDD is used to determine only a DC. For this circuit analysis, we need to find a DC analysis. Therefore, we are not using this VDD for this problem. For this case, we need to find the bandwidth, means we need to draw the bandwidth of an amplifier. This is given by the circuit. This is the mid-band gain, that is AB mid. This is the AB mid, and then for this we need to calculate a 3 dB frequencies. That 3 dB frequency may be due to the one is a CG, and then due to the CC, and due to the CS. This is related to the low frequency component, and this CW0, CDS, CGD and CGS, these components are related to the high frequency components. We need to determine one by one. For this problem, the input that cutoff frequency means, first you have to calculate a cutoff frequency of the amplifier due to the CG, that is given by an input signal, that is 1 divided by 2 pi R signal plus RG into CG. We need to substitute the values of this, then this is equal to, this is 1 divided by 2 pi into R signal is 10 into 10 to the power of 3, that RG is 1 mega, 1 into 10 to the power of 6 is multiplied with, where CG is to be given as 0.01 into 10 to the power of minus 6. If you simplify this problem, we get that frequency response. If you calculate, you are going to get a lower cutoff frequency due to the gate capacitor is given by 15.8 Hertz. And similarly, we need to calculate the cutoff frequency due to the FLC. Cutoff frequency is due to the FLC is given by 1 divided by 2 pi. These two are connected in parallel, that is RD, series RD plus RL into CC. If you substitute the values, you are going to get, this is equal to 2 pi into RD is 4.7 K plus RL is 2.2 K into 10 to the power of 3 multiplied with, where CC value is given by, that is 0.5 microfarad. If you are substituting these values, then that cutoff frequency due to this point is given by 46.73 Hertz. Okay. And also that a gain of the amplifier is varies due to the CS. Then the cutoff frequency due to LS is given by, this is equal to 1 divided by 2 pi R equivalent into CS, where R equivalent is given by, it is a parallel combination of, this is an approximate expression, this is equal to RS is in parallel with 1 by GM. If you substitute RS is equal to that 1K and GM is equal to a 2 millisiemens, this value leads to the 3.333 ohms approximately. Then that FLS is equal to, if you are substituting these values, you are going to get the value 238.73 Hertz. We got that 3 different cutoff frequencies, one is 15.8, other one is 46.73 and other one is 238.33 Hertz. Which one you are going to select for the lower cutoff frequency? Can you guess? If you plot the frequency response of this amplifier due to the various component, if you select, this is the frequency component and then this is your frequency, this is your gain. AB magnitude. This is the mid band frequency. I can say that this is AB mid, the gain due to the amplifier. Then that if you consider the alone, that CG alone, that cutoff frequency is to be about, this means plot is like this. Then this cutoff frequency 1 by 3 minus 3 dB means you are going to get, this is the line you are chosen, this is minus 3 dB from this. If you plot this, this value is equal to 15.8. If you select that only you have to choose this value is to only CC, then that amplifier response is to be like this. This value is to be about 46.73. If you consider the frequency response due to the a CS value, then that frequency response is to be like this. This value is to be around 238 Hz. Out of this, when you are plot using, this is nothing but a Bode plot. If you want to determine, select the one of the frequency component, you have to choose on this frequency, upper cutoff frequency of the all the three. Therefore, you have to ignore that effect of that CC and CG. You are choosing only the highest cutoff frequency, that is equal to 238. And similarly, we need to calculate the upper cutoff frequencies. To determine the upper cutoff frequencies, we need to calculate the input resistance Ci equal to, that is given by Cwi plus Cdgs plus Cmi, where Cmi equal to Cgd into 1 minus Av, means we need to calculate the gain of the amplifier. We know that a gain of the amplifier Av is equal to minus Gm into Rd is in parallel with RL. If you substituting that Rd and RL value, this gain is approximately equal to minus 3, where Rd and RL value is equal, parallel combination is equal to 1.5 kilo ohms, Gm is 2 into 10 to the power of minus 3 Siemens. Therefore, you are going to get this value is minus 3. If you are substituting this minus 3 into this expression, then Cmi is equal to, where Cgd is to be given by a 2 picofarad, 2 into 3 plus 1, you are going to get 4, you are going to get 8 picofarad. If you are substituting Cwi, Cgs and Cmi, then that input impedance is, input capacitor Ci value equal to 17 picofarad, and that RTHI is nothing but a parallel combination of R signal is in parallel with 1 mega, means that is nothing but a Rg value. These two are in parallel. If you are substituting these values, then this value is approximately equal to 1.5 kilo ohm. Then that FTHI, substituting that Ci and RTHI into this expression, FHI is given by 1 divided by 2 pi RTHI into Ci. Substituting this value 1.5 kilo ohms and 17 picofarad, then that FTHI is approximately, FHI is equal to 945.6 kilohertz. Similarly, we need to calculate what is the upper cutoff frequency due to this, where that we have to find C naught. C naught is equal to Cw naught plus CDS plus Cm naught, where Cm naught value, because Av is 3, therefore, if you substitute into that, a Cm naught is equal to 1 by 1 minus Av into Cgd, where Cgd is a 2 picofarad. Therefore, you are going to get 1 by 1 minus Av means 1 by 3, therefore, you are going to 0.667. If you are calculating this value, that Pf value, Ca naught value is equal to 9.17 picofarad, and Rth naught is a parallel combination of a Rd, RL and Rd. Their Rd value is not given, therefore, you can assume that Rd value equal to infinity. This Rth naught is equal to Rd is in parallel with RL, this value is equal to 1.5 kilo ohm. If you substitute that 9.17 and 1.5k resistance values, then that F H naught is equal to 1 divided by 2 pi RTH naught into C naught. If you are substituting these two values into this expression, then this is equal to 11.57 megahertz. The gain of the amplifier is to be about 3, and then 1 by root 2 if you are consider, you have two frequency components, one is 945 kilohertz and other one is 11.57. Which one you are going to select for the determining the bandwidth of an amplifier? If you plot the frequency response of this high frequency response of an amplifier, then that frequency response is given by this is frequency, this is a mid band gain, and then this is a minus 3 dB cutoff frequency. Then due to the FHI, that frequency response is to be like this, and due to the FH0, that frequency response is like this. This value is about 11.5 megahertz, this is about 945 kilohertz. Because of that, you always have to bandwidth is to be calculated to the a lower value, because this is to be, once this cutoff frequency occurs, this is not coming to the picture, therefore you choose on this value. Then the bandwidth is to be a 945 kilohertz minus a 238 hertz, that is due to the RS and CS. This is the bandwidth of the amplifier. With this problem, we conclude that we are discussed high frequency response in the today's session, and also we are discussed the low frequency response of the amplifier. Therefore, we are totally conclude with the low frequency response and high frequency response of the amplifier with this problem. In the next, we have to consider a cascade amplifier and its frequency response. For the frequency response, here in the previous sessions and today's sessions, we have discussed an individual frequency response, means our one stage of the high frequency response and the low frequency response. Now, my objective is to calculate if that many amplifiers are connected in series, what happens on the bandwidth, and also what is the effect. Because we know that already the gain of the amplifier AB is given by AB1, AB2 and up to ABN. Means you have to, if that they are in the ratio, then you have to take on a product of that voltage gains. My question is, if that gains are multiplied, what is the effect on the bandwidth of the amplifier? If even if they are taken identical transistors or identical FETs. We know that if you consider analyze one by one, if you consider this portion of this circuit, only low frequencies, this is nothing but on a low frequency response of an amplifier, then that gain AB low, we can say that this is given by AB mid divided by 1 plus J F by FL, where FL is the lower cutoff frequencies, where F is the frequency. The F is the approaches to the infinity, then this is equal to 0, a mid band gain is equal to 1, you are assuming this value. If you take the magnitude, then this is equal to, if you consider the magnitude of this, then this circuit is to be, this expression is becomes a square root of 1 plus FL by F whole square. If you substitute the magnitudes of this individual stage into this expression, then AB at low frequencies, that is to be given by your A mid is common, therefore you are going to get AB mid is common, therefore we can write AB mid to the power of n, AB mid 1, AB mid 2, AB mid 3 and so on, and then divided by that frequency response is to be given by square root of that first stage is given by, I can say that FL individual, that is by FL1 into square root of 1 divided by FL2 by F and so on. For this circuit, if you are simplify, if you are interested only on equivalent frequency response of this circuit, then we can rewriting this. What is the overall? If you are simply, if you are consider 1 divided by F by FL star by F square. If the all the stages are identical, then you are going to get a square root of that, under the same square you are going to get 1 by F L by F square into 1 and so on. For this circuit analysis, if they are going to get, if this is equal to, because if you are considering this magnitude, a magnitude is equal to, if you consider a magnitude of a circuit overall frequency, then this is given by 1 divided by square root of 1 plus FL at F is equal to FL, that is FL star square is equal to 1 by root 2. If you are squaring on both the sides, then and simplify, you are going to, this is FL by F whole square plus 1 is equal to, because this is a nth root, the n times this is to the power of n, then you take the nth root, therefore, you are going to get 1 by root 2. This is the nth root of this. You are going to get this frequency at low frequency cutoff frequency is given by of an equivalent circuit FL equal to square root of 2 to the power of n minus 1 into FL, where FL is the individual cutoff frequency at the low frequencies, and 2 to the power of n means this is nothing but that n is the number of identical stages are connected. Therefore, as the value of n is increases, then that cutoff frequency is reduced, because you are finding the roots of that, then that cutoff frequency they are defined. N is equal to 1, you are going to get this value, n is equal to 2 corresponding frequency response, and n is equal to 3, this is a corresponding. When you are considering the overall frequency response of all these 3 stages, n is equal to 1, 2, 3, then that frequency response of this amplifier stage is at this point, lower cutoff frequencies becomes. And similarly, if you are simplify this circuit at the high frequencies, high frequency response is given by, that is 1 divided by 1 plus f by fh whole square root of that. These are n identical stages. Therefore, you are going to get to the power of n magnitude, this is equal to 1 by root 2. A squaring on both the sides and then simplify, then that FH equivalent of the circuit is given by that a FH divided by a square root of FH, this is FH, this is square root of FH FL is equal to FL star, means equivalent circuit is given by FL divided by square root of 1 by 2 to the power of n minus 1, and FH is given by 2 to the power of 1 by n minus 1 into FHI. Means if you observe, if the number of identical stages are increased from this response, this is to be this individual identical stages of individual stage frequencies, then corresponding equivalent circuit is this, and if you are considering the equivalent identical stages, then corresponding finally that cutoff frequency at high frequencies is given by this point, that is nothing but FH, that is 1 by root 2 to the power of n into FHI. The cascade of the advantage of this cascade amplifier is it improves the frequency response and also it increases the gain of the amplifier, 2 factors. At the same time, the one more advantage are that in the identical stage amplifiers are connected in series, then the gain AV increases, bandwidth improves, and a input impedance and output impedance remains same as that of a single stage amplifier. Means input impedance of the multi-stage amplifier or cascade amplifiers, that input stage of the first amplifier, and output impedance is nothing but output impedance of a final stage. Therefore, without affecting the input impedance and the output impedance of an amplifier, the gain of the amplifier is improved and the bandwidth of the amplifier is improved. And I conclude this session and module 3. From the previous 4-5 classes we were discussed, sessions were discussed the low frequency response of the amplifiers in both FET and cascade amplifier, FET and transistor amplifier, and also we discussed the high frequency response of the FET and BJT amplifier, along with that a Miller's theorem, and finally we conclude with that frequency response of the cascade amplifier. If you have any queries, please contact at the email ID veru.st@gmail.com. Any queries, please contact me at any time. Thank you.